Okay, good morning, everybody. Welcome to our today's session in DYNAmore Express. Again, today we have an interesting topic. Today my colleague, Martin Helbig, who is working for our MCC, that is the Material Competence Center of DYNAmore, and he will give a talk about material characterization. And again, as usual, at the end of it, first of all, make sure that you mute your microphone. And secondly, at the end of the session, we also ask you again to fill out the evaluation form and leave us a feedback so we can improve our service in the future. With that being said, I want to hand over to my colleague, see where he is, and I'm going to pass the ball to him. Okay. Martin, are you ready?
Yes, I'm ready.
Okay, I give you the ball.
So, okay, I think you can see me now. I will switch off the camera and we'll start the presentation. If I find out, 1 second. So, can you see the slides right now?
Yes, we can see you.
Okay. Full screen mode. So, do you see the full screen or do you see with the
presentation mode we can see here?
Presentation mode. So okay, so that means it's working, yeah? Fine.
No, actually, we see both. We see the presenter mode. We see the presentation and the small one. Do you want to have it like this?
No, these are the. Okay, just wait. I will start again. And now we should. Oh God, what's this? Sorry. I'm sorry.
That's okay.
Now.
Yes. Perfect.
Now. Okay, so we are ready. Okay. Hello, everybody. Welcome and thank you for using your time. Today I will talk about the introduction to material characterization. This workshop was done originally in 2000 in Bamberg. Yes, and I will give you a short introduction to the material characterization. My name is Martin Helbig. I work for DYNAmore since 2014. I did the slides together with David Koch. He's my colleague. And this is the content of the talk. So I will give you a short introduction, some motivation, why you should do some material characterization. Then for sure, I will talk about this DYNAmore Material Competence Center we're working for. I will give you a short introduction to plasticity, which means I will explain two material cards, MAT24, our working horse, and an anisotropic material card. Then I will come to material calibration, which means how to get the results from your test to your material card. I will have a few slides about the testing and modeling of foams. And in the end, I will talk about the polymers, which is more or less my topic here, where I'm working for most of the time. So I will talk about SAMP-L. This is a semi-analytical material law for polymers. And since last year, we have also a light version of it, which is a little bit faster than the original SAMP model. So I will show you, I think, 1 or 2 slides about it. So let's start with the introduction. So we have a challenges in the automotive industry for efficiency lightweight structures. This means we have to fulfill the safety requirements. We have to reduce the weight, and also should be have a look at the costs. And these things are done with newer materials since the last year. So we have composites, high-strength steels, light alloys, and polymers. And if you characterize this kind of materials, you should have a look especially here at the plasticity, anisotropy, and we have taken into account also failure, damage, Sometimes the fracture grows, and the debonding is a big issue. Today we are talking only about the plasticity, a few slides about the anisotropy. That's what we will see. So we have, for some typical materials, some typical phenomena. For metals, we have a linear elasticity. We have an isochoric plasticity. We have sometimes an isotropic or an anisotropic yield behavior. We can have a strain rate dependence, and we also should take into account damage or softening for plastics or polymers, thermoplastics. We also have a viscose elasticity, which means that the elasticity is depending on the load velocity. We have an isochoric or sometimes also a non-isochoric plasticity. This means our volumetric strain or macroscopic volumetric strain is increasing with an increasing deformation. Polymers are strain rate dependent, most of them. And also we have some damage or softening on polymers. Then we have foams. Foams also kind of polymers, but a special kind. Most of it's modeled with, they have a viscose elasticity. We have a low stiffness, a low strength, and a low Poisson ratio. And a little bit different are these crushable foams. They're also characterized a little bit different. And we have brittle materials like concrete. So we have a linear or a non-linear elasticity. Non-linear elasticity means you also you cannot describe directly the connections between the stress and the strain by one parameter. So you have something like a deformation path. We have rubber materials. They are hyperelastic. Hyperelastic means they have very large elastic deformations, like everybody knows from rubber. These elastic deformations are also depending on the loading velocity. So we have viscose elasticity. They are nearly incompressible. This makes some problems in compression, for example, and this Moulin effect. You will see this effect if you do some loading or unloading tests. For composites, we have a nonlinear elasticity, anisotropic effects, strain rate dependence. We have a heterogeneous structure and also should take into account the damage or the fracture behavior of the composites. So what we are doing here is with our material law, or with this constitutive law more or less, we describe the connections between the stress tensor sigma and the strain tensor epsilon. So to describe how these two second order tensors are connected together, we use this constitutive operator. In the easiest case, you only have to use this Young's modulus, as you see here in this formula, but most of the time it is a little bit more difficult. So you have some variables like plastic strain, strain rate, temperature, etc. So this means when you define the material parameters, for example, for hardening curve for a material model in LS-DYNA, you actually indirectly pre-describe the constitutive law. So in easy words, you only do this material characterization to describe or to find a good constitutive operator. And if you don't do it, you will not get the right connections between the stress and the strain tensor. This means you will not get the right solution of your finite elements simulation. So this was the introduction. I come to DYNAmore's Material Competence Center. DYNAmore started in 2014 doing some tests, or doing some tests in a bigger way, more or less. So they started in our office in Stuttgart-Vaihingen. And with the time, this was growing. So I started in 2014, and then 2015, my colleague David Koch came to the company. And in 2016, I think, our third colleague Christian Il came. And then after a while, the rooms at the office there were too small, so we moved out last year to our new rooms here in Leinfelden-Echterding. And when we moved out, we also find a new name for our laboratory services. So this is right now the Material Competence Center. And the idea is that we are offer you calibrated material cards and the best possible modeling techniques. That means we do some tests on metallic materials, also the failure prediction with Gizmo, eGizmo, DM, and so on. We do some tests on polymer or composites, elastomers. We had some experience with glass, like float glass, terminal or chemical temperature glass, ceramic materials. And also we start testing some connection technologies like puncture foam or spot weld or adhesives. So this is the testing equipment. We have a universal testing machine for quasi-static tensile tests. We can do this machine some tension tests, compression, shear tests, biaxial tests, bending tests, and also some cyclic loading, which might be interesting if you have, for example, a rubber material. We can do some optical strain measurements with our DIC system. We have a 5 megapixel 3D Aramis system. This means we can measure directly during the test the whole strain field at the specimen. Additionally, we also have an extensometer, which means a clip gauge to measure the strain directly between 2 points. With this extensometer, you don't have any post-processing stuff. You get directly your results, and you can have a higher resolution in time, especially for elastic materials. It makes some sense also to use the extensometer. And here on the right, you see the pendulum. It's from 4A, a company from Austria. This is a very easy and quick way to do some bending or compression tests for plastics, foams, or composite materials, for very light materials, to get very fast and easy dynamic characterization of your material behavior. So this is some slides here, some bricks for the tensile tests, bending tests, here compression tests or biaxial tests. And that's what we can do here. If we are not able to do it, we know some guys who can do it. So if you have any questions about material casts, so please give us a call. So enough of this commercial stuff. So we come to this von Mises plasticities. I have 2 cards here. The easiest, MAT 003, plastic kinematics. This is the easiest and a very fast material card you can use if you have a bilinear isotropic material, and you can switch between isotropic and kinematic hardening. And the next point will be this MAT 24, a MAT piecewise linear plasticity. This is the working horse. This card is very, very often used in LS-DYNA. And the material law itself, it's very fast, and also yes, it works very fine. Actually we use it for metals and also for plastic materials. So we start with this MAT plastic kinematic. As I mentioned before, it's a von Mises material. It's a bilinear elastoplastic model for kinematic and isotropic mixed hardening, strain rate dependence. We have an element deletion, it's possible, and it's very simple and fast material model. You start here with this material ID, you put in your density, your Young's modulus, Poisson ratio. This is the yield stress, this is the tangent modulus. This beta, this describes you the hardening, if it's isotropic or kinematic hardening or something in between. Then we have these parameters in here, SRC, SRP. These are for the strain rate. Dependency, you can describe the strain rate dependency of the material with the Copper-Simons function or law. Fs is the failure strain. This means when you reach such a strain, the element will be deleted. And Vp is for the formulation of the strain rate. The idea is to use this material instead of a pure elastic material to avoid very high stresses, which are possible at very large simulations. and therefore you will not get an extremely high stresses if you have a little bit of higher deformation, elastic deformation. So because you get into yielding, or you can delete your element, and it's also very fast, so you will not lose any time if you still stay on the elastic regime. So then we come to MAT24, the working horse. I think most of you already work with it. It's the same. We start here with the material identification, the density, Young's modulus, the Poisson ratio, and you can use it also as a bilinear law. This means you have a yield stress in here, and you have a hardening modulus here, this etan. In our times, most of the time we don't use this bilinear way. The second opportunity to describe the yield behavior is just over 8 points. 8 points to give in the plastic strain and also the corresponding stress value. This is something historical. In our days, we use a load curve to describe it, and here this is this LCSS. This is a load curve or a table you give in to describe the yield behavior. We have in MAT24 a failure flag. This means when kind of a plastic strain is reached, the element will be deleted. There's also a minimum time step for the automatic element deletion. We can describe the strain rate effects with the Copper-Simon's law over the parameter Cp. We can also describe it over a table here at LCSS. And there's also a third opportunity to describe the viscoplastic behavior over a load curve. It means you put in a load curve with the strain rates and the yield stress and some kind of a scaling factor to describe which scales you the quasi-static yield curve LCSS. And you also can switch between different rate formulations. Yes. Okay, this is the way we put it in today over the load curve. You define the curve. Here you have your plastic strain values, and here's the true stress. And I will show you later how to come to these curves here. So this is the way actually we do it every day and to describe the yield behavior with MAT24. So this is the summary of MAT24. This is the working horse and crash simulation. The material is available for shell and solids. We have a load curve based input, which makes the material model very flexible. You don't have any kinematic hardening here at MAT24, therefore you have to use MAT225. The points between the rate dependent curves are interpolated linear or logarithmically. This makes some sense depending on how big your range of the strain rate is. The load curves are extrapolated in the direction of the plastic strain by using the last slope. You have no extrapolation is done in the direction of the strain rate. This means the lowest curve defined is used in the current strain rate, also if it lies under these input curves. It is possible to use negative or zero slopes, but it should be generally avoided. Sometimes for plastics, it is useful also to use a negative slope. So we come to this anisotropic plasticity. This anisotropy comes from some process stuff which you do like rolling, for examples, and it is described over this Langford parameter. I will show you 2 slides later. So this is how you can find out if you have an anisotropic material. I showed you here. On the left side, we have a sheet, a metal sheet, and we cut out some tensile specimen at different orientation or at different angles due to the rolling direction. And then we can do some tensile tests, and we see the results that depending on the removement or on the angle, we have some different engineering stress strain curves. And these are defined, or they can be described, this difference here, over the Langford parameters. And this can be done with a MAT36, this Bala model. Here are this description of this Langford parameters. It is the ratio between the strain rate in width direction divided by the strain rate in thickness direction. And most of the time you don't know the strain rate in thickness direction. Therefore, you can assume that your volume is constant, and you can describe the strain rate in thickness direction over the strain rate in length direction, or as the sum of the strain rate and length direction and the strain rate in width direction. So, and this is the way we use it here. And this parameter shows you if it's 1, that is necking and the thinning of your materials are comparable. If you have slopes more than 1, it's less necking, more thinning. If it's bigger than 1, you have more necking and less thinning. So this R values itself, if it's the same, and they are quite 1, you have an isotropic material. And if you have the same parameters here for R0, R45, R90, you have an anisotropic behavior in the thickness direction. And if all 3 parameters are different, you have an anisotropic behavior in the plane and in the thickness direction. And these parameters you need to describe the material behavior. So we have different anisotropic materials in LS-DYNA. There's a lot of different material laws. I will only talk a little bit about this MAT 36. But we also have some trainings about modeling of material, metallic materials. If you like to, you can ask the guys for some training, and they will explain you the detail of each of these material laws. So this is how this card looks. This is the 3-parameter Bala model. You start with the material identification, a density, Young's modulus, the same than the Poisson ratio. And this is the most important parameter here, this HR. This is the hardening rule. And you have a lot of choices in this MAT 36. Therefore, the other parameters, P1, P2, AB, CB, and so on, HP, they are changing depending on what you have to put in here as a HR factor. So you will see it at the handbook that you have a lot of choices. So this means this other adjustable parameters, material parameter 1, material parameter 2. We have the iteration flag, and we have here, this is the exponent of the yield surface. Important for you is more or less the R values you put in here directly are for 0 direction, 45 direction, 90-degree direction. This is the load curve. For the 0 direction you put in, but if you change another HR, you can also put in some other curves in here, depending which parameter you set. So this is how it works. We see here we put in some values for the R values. This is the formula which is given due to this material law by Bala and Lyon. And what you have to find out are these parameters A, C, H, and P. You put in here your R values, your sigma, your yield curve, and you put in here this M, this hardening behavior, and then over an internal fit, you get these parameters which is needed here for the description of Bala. It calculates you the stress strain value, and this more or less is the way how your yield surface is expressed. So if we change a little bit, you also see we have a change here in these stress strain curves. They had an extension of MAT 36 with HR7. Done with Mr. Fleischer from BMW. HR7 means that you have hardening in the 3 direction. That means you create a hardening curve for from the tensile tests in 0, 45, and 90-degree directions. And you put in your hardening curve directly here at P1, P2, and here is for the 0 direction. It's the hardening curve in the 0 direction. And it's also possible here to have a curve of this Langford parameters as a function of the plastic strain. This means you calculate your R values as a function of the plastic strain to describe the yield behavior depending on the plastic deformation. This is how it looks like for two different parameter sets. Normally your yield surface should be convex, but if you use some special kind of parameter combinations, it is also possible that your yield field is no more convex, and this can avoid some. This can cause some problems. You can get a lot of problems if your yield surface is not convex. And with this experience, DYNAmore or LSTC went on, and this MAT36E was developed also together with Mr. Fleischer. And this is an extended formulation with some different input format. It's available since LS-DYNA version R9. More or less important, or the big difference here between this MAT36E and MAT36 is the Hosford parameter. So this parameter here, this is the most important. If you set it to 0, you get the same at MAT36 and this HR7. This means you can put in the load curve for each direction and also the curve of the Langford parameter for each direction, and you will get the same results. And if you set this Hosford parameters to 1, you get a little bit different behavior. This convex yield surface is internally directly calculated. This is shown in here as Hosford 0. We have this set of parameters we've seen before, and the yield surface here is not convex, and this is Hosford 1. And internal iteration is taking place, and the yield surface is convex. And the results we see in here for this notch tensile test with Hosford 0 and this non-convex yield surface, we get some problems in here. And if you use this Hosford 1, we get a smooth curve in here. The problem is if you ever had your material card with Hosford 0 or the conventional MAT36 card, you have to do some refitting to get this Hosford 1 and a little bit of smoother behavior here. If you have any problems with this, just ask our support. So we come to the material calibration. Depending on what you want to see is, or depending on which problem you have to do some different tests. This is a very short matrix. This is what we do normally in our everyday work. So we use quasi-static tensile tests more or less for everything. So for elasticity, viscoelasticity, you have to do some static tensile tests. Plasticity, viscoplasticity, and also to describe the damage behavior. Compression tests, they are useful for rubber or foam materials. Shear tests, they are useful if you have the damage description with gizmo, for example. If you have viscoelastic or viscoplasticity, you have to do also some dynamic tests to describe the strain rate behavior. And the cycling tests are useful, for example, for viscoelasticity. So these tensile tests are, in my opinion, one of the most important tests. So you have a huge range of different kind of tensile test specimens, some different geometries. Important for each geometry is that you have the initial length, and between these 2 points here, the strain is measured, and this should be a given. Otherwise, you cannot calculate with such a test result. So here's just an example. Normally, the customer chooses the the kind of specimen he wants to use, or which is common at his company. This means he gives us the dimension, or we can, yes, he gives us the dimension. And you have this gauge length. These are the 2 points where the strain is measured between. We have fixed support, so this area here, for example, is not moving, and then we have the other area is moved, and normally use some quasi-static tests, depending on the standard you use. It is described how fast quasi-static tests are done, and what you get is a result in here. This is more or less the red curve here, and therefore you do some smoothing, some filtering, and so on. But important is that you should have a look also at the raw data. So if you get any tests, just ask for the raw data. Then you see the influence of the smoothing, filtering, etc. And for this material calibration, you can use some average of all test curve, or you can just use one test curve, depending whatever you like. It's up to you. So this then you start with your test results. So you get this engineering stress strain curve. You measure the Young's modulus in here. This is the initial slope. It's also depending, and it's also described in the standard you use. So you defined your Young's modulus, and up to a certain point, you say, okay, this yielding starts, and you measure your Young's modulus, and also your yield stress. At this point here on the right side, you see this necking initiation. This is a very important point in here. This is the maximum of this engineering stress strain curve, where the slope is 0. At this point, you also have to find out this ultimative strain. So this necking initiation point is important later if we create the yield curve. So okay, then we calculate the true stress strain curve. The difference is that the engineering stress strain curve is still depending on this initial area and also on this initial length. And if we create the true strain curves, the true stress curve, true strain curve, it is depending on the current area. That's a big difference between if you have some necking, the area is decreasing. And the true stress is more or less the logarithmic strain, which can be calculated in easy cases here as a function of the engineering strain and the ln. Engineering strain plus 1 and the ln of it. And we see here it's a different, this is the true stress strain curve, and it's increasing compared to the engineering stress strain curve. Here we have a decrease, and we need the true stress strain curve to create the yield curve. This is the way you can calculate the true stress for an easy one-day case. It's the engineering stress multiplied by 1 plus the engineering strain. You can directly calculate your engineering, your true stress from the engineering stress. But this is the assumption of a constant volume. This means for polymers, sometimes you need another way to calculate your true stress curve. And then you go on and subtract the elastic part of the true strain. And with the subtraction, you get more or less your plastic strain. And the plastic strain as a function of the true stress is what you give in as the yield curve. And this can be done until the necking point. And after the necking point, you don't have a uniaxial stress state. This means you need some reverse engineering, some extrapolation of your yield curve, and therefore some analytical functions were done. And in the past, originally, they were done to describe the whole yield behavior. Nowadays, we use it still to describe the yield behavior after the necking point. Here are some different formulas: Ludwig, Swift, Gauche, Voice, Hockett-Sherby, and so on. At the moment, or we very often use Hockett-Sherby to describe the yielded behavior after the necking point. We do it with some reverse engineering. That means we simulate the test the tensile tests, and we compare these simulation results to the real test results. And at this point where we get the best agreement between these two stress strain curves, this engineering stress strain curves, we say, okay, this is our set of parameters. So this is an example again. As I said before, you calculate the true stress strain behavior here. We get the true stress. And here we have the plastic strain, which means that you use the engineering strain plus 1, the ln of it. Then you have the true strain, and you subtract the elastic part, which means this is the engineering stress divided by the Young's modulus. And this means that you swift your curve a little bit to the left side, as seen here before. And also this point here, this HE, is moving a little bit left. And after that point, you start to extrapolate, depending on which formulation you use. Here, for example, the Hockett-Scherby. But you have to consider at this point here that you have a C1 community at HE. This means your Hockett-Scherby equation here is reduced to two parameters. You need this parameter A and B for this C1 community, and you only have to find out the right set of the remaining parameters C and N. And that's the way more or less to get your yield curve for tensile from tensile tests. One thing you have to consider is that after the necking point, after the maximum of the engineering stress strain curve, your results are depending on the element size. This means, here's an example we used at our trainings. We have two tensile specimens with some different element sizes, and we see we got more or less the same stress strain curve until this point, and then we get a difference in here after the localization, and you can handle this element size dependency by using kind of a damage description like Gizmo, for example. So in Gizmo, you can give in a curve with different element sizes and a factor that you get the same stress strain curve after the necking point. It's regularization. Okay. We come to foams. Foams are becoming more and more popular since the last 2 years, I think. One material law to work with foams is Fu-Chang-Foam. It is very nice material law, and it's also very easy to get your data into this material card. What we are doing here for testing is we use our pendulum. We can have some dynamic velocities here from 0.5 up to 4.3 meters per second. This is the pendulum arm here. There's a mass on it. We can change this mass to get more impulse to our specimen. Here is the specimen fixed, and the idea is that you have such kind of potential energy in here. So you put out the arms in here to get a height, more or less, to get a potential energy. And then you remove a brake, which is fixed in here, and the arm swings directly to the specimen. There's no engine on it or something. It's just due to the height here. And your potential energy moves to a kinematic energy. And here you can calculate your velocity when this pendulum arm hits your specimen. And from this velocity here, you can directly calculate your initial strain rate. This is how it works. So for foam, you use some different lengths of the specimen. You can choose some different velocities. We also can do some quasi-static compression tests at the tensile testing machine. And you see here you get some different strain rates with this quite easy formula in here. So this is yes. Normally we don't do so many tests. We do about 3 or 4 tests at different strain rates. And the result is you get from the pendulum is this here. Here you see on the left side, we have a stress strain curve for different strain rates. So we have the stress in here on this axis. We have the strain rate here. and this is the strain measured at the pendulum. And if we have a look at these curves, we see that the strain rate is not constant. The strain rate here is decreasing. Also for the other velocities, and this the material caught itself needs curves at a constant strain rate. Therefore, we use them LS-opt here. We see the picture of LS-opt. It creates you a surface over these curves here as a function of the strain rate, the strain, and the stress. And then you still can cut out curves here at a constant strain rate. And these curves you can put in the input of MAT38 of MAT Fu-Chang-Foam. And if you put in this curves here, you have to be sure that the curves starting with 0. And you put in some engineering stress strain curves. So and you should be have a look that you have the same points in here. It makes it easier for this material law at the calculation. So you don't need any interpolation algorithm to get a value if it's between these different strain rates in here. And this is a very fast and easiest way to create this material cards for foams. So I come to the last points, the testing and modeling of polymers. I will give you a very short introduction to MAT SAMP-1. And then I will introduce the new SAMP light model. SAMP means a semi-analytical model for polymers. I think it was developed 10, 15, 20 years ago. And it's becoming more and more popular. So the idea of SAMP is that you can put in every kind of load of stress strain curve you get from your tests. So this means if you only have tensile tests, you put in only one curve in here, and you get a von Mises behavior. Your yield surface is still the same here at the area of the compression and this Q. And you have a von Mises behavior, so it behaves the same like von Mises. So if you have a second test curve like a biaxial tensile test, a compression test, or shear test, you can also put in a second point, and you get a Drucker-Prager behavior. So it's a Drucker-Prager cone in here. And you can do it up to 4 curves you can put in. This is shown in here. So some curves for biaxial tension test, tensile tests, some shear tests, and some compression tests. And the yield surface will automatically be created, as we see here. And there's also a flag that we don't have a yield surface like this. It means it switches then to this, or it moves the shear point to this. And the idea of the material is to describe the yield behavior of a polymer as good as possible. We can put in a plastic poisson ratio. This means it is possible to take into account a non-isochoric material behavior. Example for grazing, you need it that when your macroscopic volume is increasing, so you have to change the plastic Poisson ratio. And this is the SAMP light model right now. It is a slim form of the SAMP model. It is also strain rate dependent, but you can also put in a second strain rate dependency on the compression. This is a difference between SAMP. You can use a constant or a variable plastic Poisson ratio. The shear or biaxial tests are not incorporated, so they are not taken into account. And also damage or failure is not available in the SAMP light model. And usually you cannot directly use your SAMP-1 cards in SAMP light. So you have to be a little bit doing some kind of transfer if you want to use your old SAMP cards in SAMP light. SAMP light is faster, much faster than SAMP. And this was the reason to create this material law. So here we see the put in. This is just from the handbook I copied out. Here described is the different curves you can put in for this SAMP material card. And also in the SAMP-1 model, you can create some damage behavior. but it is also possible to use mudded erosion for the SAMP model. So the new SAMP-Lite does not have any failure description, so we have to use a mudded damage or mudded erosion, for example, to describe the damage behavior, and we only have to put in 3 curves, if you put in 1 curve, you have also the same, it's van Mises behavior, with 2 curves. With the compression curve here, you have the Stoker-Prager behavior, and additionally, you can create a curve here for this plastic Poisson ratio. And this is a short example here. I think I showed it sometimes at some different conferences. We see special here is a tensile specimen with this geometry, and these are the bending specimens, and we measure the strain at these. And we have 2 different measurements. So this is the clipping length and the measurement length here. It's 40 millimeters. First, I started just with a MAT24 card and a gizmo. More or less, the gizmo was not needed because there wasn't so much damage. So, and the results are these here. We see the force displacement curves of dynamic bending tests. The thick lines are the experiments, and the thin lines are the simulation. And for the lowest velocity here for this dynamic bending test, we had, I think, a good agreement here for the first step with the easy MAT24 law. But we get a little bit different here for the higher strain rates. So the idea was to improve the agreement by using the SAMP model. So therefore, I created this plastic Poisson ratio curve. Here we see the input curve for the. This is the plastic Poisson ratio as a function of the plastic strain. And how can I get this curve? So I used the volume strain. This is the sum of this Henke strain. Is defined as the volume strain over the true strain. And these 2 strains are here also considering the elastic part. Therefore, we have this gap in here, and also we have this increase for the lowest curve. So in black, we have the result of MAT24 if we have a look at the volume strain over the true strain. So what we see here is this increase. We see it's only due to the elastic deformation. For the plastic deformation, it means that this curve stays the same. Then I used SAMP with a constant plastic Poisson ratio of 0.5 and got the green curve, and I got the same result for MAT24 and for SAMP. This is how it should be. Then I said, okay, I try another value of the plastic Poisson ratio. It's 0. That means we have a real huge increase of the volumetric strain. And this is what we see here with the blue curve. We see here when the yielding starts, it is the volume is increasing dramatically. And then I went to the experiments. I have a look at the experiments, and I got the black curve here from the experiments. And then I used the curve of this plastic Poisson ratio and the plastic strain, created some points in here, and moved these points until I get these results here. This is the point where the yielding starts into this non-parallel areas of the specimen. So if we have a look up to this, we have a good agreement between our experiments and the simulations. I did it just with a 1-element test. And this is the results. This is the influence, more or less. If we compare here MAT24 and the SAMP model, we see that we have a different strain perpendicular to the loading direction. So the minor strain is here, it's much lower compared to MAT24, and this can be important, especially for large models, for example, when you have an increase of the volume. So the next step then was to take the compression into account. I did it just by reverse engineering and simulation the bending tests. This means from the green curve I get to the red curve. There should be no results for tensile tests because it is the same as before here. We still hit the point. But if you look at the compression, at the bending tests, we see there's a large influence, more or less. We can, we can improve the test results here, especially for the lowest strain rate. and for the second one. And we also got to improve for the higher strain rates, just taking into account the compression behavior. This should be a small example how you work with SAMP. The same could be done with SAMP Light. So if you have any questions, or if you want to have any courses or something, you can have a look at our homepage. So we have a homepage in here. It's www.dynamore.de, and we offer some training, some seminars, also like DYNAmore Express. You can ask the two guys here, Mike Schenke, who introduced the session, and Karina Sieber, who's responsible and organized the whole stuff. So more about DYNAmore, LS-DYNA products, you also can find at our homepage, or at DYNAmore support. We have some examples here at DYNAmore, DYNA examples, the conference papers. You can find our DYNA look. Any tutorials for LS prepost you find under lsdc.com, LSPP, and also some examples tutorials for LS opt. This is the guys here. I mentioned my colleagues at the Material Competence Center. Here's our boss, Professor Dr. André Haufer. He's organizing the whole stuff, and we're doing the work here. This is me, it's Martin Helbig, Christian Ilk, David Koch. They're responsible for metallic materials and also for class. Yes, and this was the same I showed before in the slide. So if you have any questions, just please contact me. Thank you very much for your attention.
Okay, thank you, Martin. We have some questions in the chat where I just ask you in favor of the participants. So the first question, let me think, what was it? The first question was, would a horizontal slope result in strain location? Do you know? I mean, I was thinking about this. I'm not sure. I think it's not working, right? I'm not sure.
I'm not sure. You should try it out.
I think you need strain hardening. I'm not sure.
Yes, to result a necking or something. Yes, I also think so.
Okay. The next question is, how do you measure the volumetric strain in the experiment?
Okay, this is a good question. I go back to the slide with normally we use the IC system to measure the strain. Therefore, you can measure the strain. You can measure the whole strain field. This means the strain field in the loading direction and also perpendicular. You can measure the whole strain field. And then I take the average over the strain field, more or less, or the field where the necking starts. I use the area and make the minor values of this area of the deformation. It means I have this minus, or the average value of the strain in loading direction and perpendicular to the loading direction. And then I assume that the is constant. This will not work for plastic if you have a non-isochoric behavior. Or I assume that the strain perpendicular to the loading directions are the same. This means the strain in width and thickness direction should be the same. Otherwise, you have no chance, or you have to measure the strain also in the thickness direction. Therefore, you need a second DIC system. So normally, I assume that the strain and thickness and width direction are the same to measure the volume strain.
Thank you. There is another one which is a bit long. Why you can't get directly the true stress strain curve directly from the tensile specimen, a tensile testing machine, after converting the force displacement curve internally instead of using the Excel sheets?
Okay, again, this means you directly measure the true stress strain.
Why you can't?
You can do it directly if you know your Young's modulus before, because you have to subtract the elastic deformation. But it is possible, but it's not possible after the necking point. This means if you have only a small inelastic deformation, you can also directly more or less measure your yield curves or your true stress strain curves. yes, it should work. If your volume stays constant, this should work. This means you can directly measure your yield curves. Until the necking point. After the necking point, you have to do some reverse engineering, and this takes some time.
Okay, which material would you suggest for anisotropic soft materials? For example, human bladder wall? I don't know what it is, but do you have any suggestion?
No. We should have no. I have no idea. We should have a look. We have also a lot of anisotropic materials. The anisotropic materials I showed were especially for metals. But there are some possibilities, but we should have a closer look at this topic. Maybe you can write us an email to the support of LS-DYNA, and then we will have a look at this topic.
That's also what I suggest, because we're almost done with the session. If you have more questions or later some questions pop up, just send us an email. By the way, so let's just do a quick one. Is it possible to use biaxial test data in MAT24?
You can use it, yes, but actually what you put in are the yield curves are just from uniaxial test data. This means you have to convert in any kind of way your biaxial testing data to a uniaxial testing data. So it's a little bit different, I think. If you have some data from biaxial testing, maybe you have also some data from the uniaxial testing, and then you can still use this data from the uniaxial tensile testing and simulate the biaxial testing, and you can have a look how good it describes this biaxial behavior. Otherwise, you have to use a more complex material law.
Thank you. So we just have two more, and then we're going to close the session or finish it. And this is related to cyclic testing. In application with more than one cycle, the cyclic stress-strain curve becomes quite different from the first loading. How do you model this? So how do you change?
Therefore, you can sometimes use a viscoelastic material where you can create this prone series. It means you have a special kind of damper and springs. They are parallel, and you can you use different parameters for this dampers and spring to have this viscoelastic effects. This is possible, especially for rubbers. It is very important to take this into account. Therefore, you have some different advanced rubber materials where you can use it, and you also can do it in SAMP, the SAMP-1 model, and I think also the SAMP light model is possible to taking the viscoelastic effects into account. I don't know if you can directly put in the parameters of the Brownian series, but it is possible to fit this testing results to the material.
Okay, and the last one, you mentioned that matte elastic should never be used, and matte plastic kinematic is recommended. Yes. In case you see strains are low and well within the elastic range, is there any disadvantage still to use the material card?
No. If you don't, if your model works fine, you will not have any problems. But for larger models, it is useful to use the other one, this matte free, to avoid this high stresses if you have any numerical problems sometimes. This can happen, especially if an element fails. You can get just a very high deformation at one point, and then you get a very high stress, and sometimes this causes some numerical problems. This can happen, and to avoid this, you can use this matte free. This was the idea, what I want to say.
Okay, so with that, I'm closing the session. I will post a link to the evaluation form in the chat. So please fill out the evaluation form, because it helps us to improve our session in the future. And with that being said, whoops, that was not supposed to be. Yeah. With that being said, I will close the session and then see you next time. Soon. Sorry. And yeah, fill out the affiliation form and see you next time for the next webinar. And if you have questions, contact us at support@DYNAmore or check out DYNA examples, DYNA look, DYNA support. And also we're going to post the slides and also we put the video online afterwards. So thanks again for your attention and bye-bye. And thank you again, Martin.
Yes, thanks. And thanks for investing your time.
Bye-bye.